So now let's develop the equations for the conservation of momentum. If you remember back to when we started talking about the Reynolds transport theorem, we said that if capital B, representing our extensive property, was momentum, then lowercase b, the intensive property, would be velocity. Or more formally, capital B is a vector, because momentum is a vector, is equal to m times velocity, and lowercase b, the intensive, is just equal to velocity. If we substitute these into the Reynolds transport theorem, we see that the time rate of change of the momentum of a system, and I'll write it like this, is equal to the rate of change of the momentum in the control volume plus the rate at which momentum enters and leaves the control volume integrated over the control surface. So we substitute in B and we get rho v dot n hat dA. This last term is a little bit confusing because we have two velocities in there. Remember, this is the rate at which the fluid is crossing the boundary, and the fluid crossing the boundary has a certain amount of momentum, which is this term here. And so when you integrate the momentum in any fluid particle times the rate at which it's crossing the control surface over that control surface, then you end up with the momentum that's carried in or out of the control surface, depending on the direction of the velocity. Here, this is pretty straightforward. We see that momentum shows up directly there, and the extensive property here on the left shows up here. Now, what use is this? Well, if you remember back from physics class, this fairly well-known equation, F equals ma, let's write it in vector form like that. Well, we see that ma is just equal to m times dv dt, and we can write, if the mass is constant for a system, which it is, then this, we can take the m inside the derivative, and we get d dt of mv hat. So knowing that, then, we know that the rate of change of momentum of a system is equal to the force acting on that system, or as we usually talk about, the sum of the forces acting on that system. We can make that direct substitution into the equation above, and we see the sum of the forces acting on a system is equal to all of the right-hand side of our Reynolds transport theorem. Now, in general, we'll have many kinds of forces acting on our control system, and these can include gravitational forces, viscous forces, pressure forces, and then other special forces, magnetic forces, and such, if the case arises. Now, when we derived the Reynolds transport theorem, if you remember, we started off with the system being coincident with the control volume, and then we developed the formula from that point. What this means is that for the consideration of the Reynolds transport theorem, the forces on the system can be translated to the forces on the control volume. So that means that we can calculate the forces on the control volume, and they end up on the left-hand side of this equation, and then we can calculate what's going on with the momentum within the control volume and the momentum crossing the control volume boundaries here. Let's work an example to demonstrate this.